Jinha will talk about some new theorem of someone else, by Kalai and Wu and Parson. We've been thinking about this problem, but we already discovered that someone else proved it, and she will explain the paper. Please.
Thank you for introduction. Yes, so I want to talk about very recent results. So the paper is uploaded on this November on arXiv, and so I will focus on the proof idea and proof method of their result. So about result, the reason why that I'm interested in this problem, so in this September there was another paper on this arXiv. So that proves a weaker version of this Kalai-Meshulam conjecture. And after I read the papers, so I mean the statement is topological, but I mean it's related to graph structural theorem. So I asked Zhang whether he knows something about this problem. And surprisingly, only after 2 months, this conjecture is solved. So anyway, so Zhang wanted to know the proof method. So okay, so I will first define. So we have a graph G, and we say graph G is ternary if G does not induced cycle so we say if graph is ternary if this graph does not have an induced cycle of length divisible by 3. And the statement of Kalai-Meshulam conjecture, before that I will define f sub g, reduced Euler characteristics. And it's the number of independent sets of even size and minus number of independent sets of odd size. And the statement of Kalai-Meshulam conjecture is if a graph G is ternary, then the absolute value of this Euler characteristic is bounded by 1. So that was the conjecture. And actually it is proved by Chodnocki and Scott, Seymour, and Zucker in 2020. And so this is just one version of Kalai-Meshulam conjecture, and there is another topological version of Kalai-Meshulam conjecture. So I will talk about the topological version. So before stating that version, so I need some more definitions. So okay. So first of all, I of G is the independent set, independence complex of graph G. So here, independence complex means simplicial complex on vertex set. This is our independent set. Okay. Then also I will denote this beta I tilde of this complex. So it is the i's reduced Betti number. So I will not explain what is Betti number exactly, but I mean, let's just say briefly. So it's dimension of I-dimensional homology group of this independence complex, and the meaning of this Betti number, I-dimensional reduced Betti number, is the number of I-dimensional holes in this complex. So it's roughly saying that number of I-dimensional holes in complex. Okay, and then here's some remarks.
The number of I-dimensional, minimum number of I-dimensional holes that can generate the cycle space of I-tree.
Yes, I know. But I mean, so I said roughly. Okay, the number of independent I-dimensional holes. Okay, so here's some remark. So our Euler characteristic is equal to the alternating sum of Betti numbers. So it's just followed from dimension theorem that gives, so consider exact sequence which gives homology group, and then consider the dimension theorem, then we can obtain this. And then also define now total Betti number is just positive sum of all Betti numbers. Then of course f sub g, the absolute value of f sub g is bounded by total Betti number. Okay, now we can define another version of Kalai-Meshulam conjecture. So the assumption is same. So if our graph G is ternary, then first this version, so this is bounded by 1, and second, total Betti number is also bounded by 1. And there's also more stronger version. So our independence complex is either conjectable or homotopic equivalent to a sphere. So here 3 implies 2. Because if our complex is contractible, that means it has for all dimension Betti number should be 0. So that means total Betti number is 0. And if this is homotopic equivalent to a sphere, let's say it's equivalent to some d-dimensional sphere, then only beta sub d is 1, and for the other dimension it should be 0. So total Betti number becomes 1. So 3 implies 2. And also, as I mentioned before, because of that, 2 implies 1. Okay, now here's some short history about this conjecture. So first, as year 2017, he proved a weaker version of 1. So here, weaker version means, so here the assumption is our graph is ternary. That means there is no induced cycle of length divisible by 3. But here we assume that G does not have a cycle. So here, even it is not induced, it is not allowed. So assumption is a bit stronger. And Chudnovsky, Scott, Zimmer, Sparkle, they proved this version 1. And Engstrom in this September proved weaker version of 3. So here, look, weaker version means that they mean here. And also, very recently, Wu and Zhang, they proved this version 2. So the only remaining things is number 3. So almost solved. So anyway, I want to explain the proof idea of this proof of version 2. Okay. So here's very basic and also very useful tool. So usually to compute some independence complex or matching complex, it's very useful. So their proof idea is basically use main arbitrary sequence many times. So yeah, just basic technique. So here's the statement. So we have a complex K and say that it is a union of 2 simplicial complexes. So here are simplicial complexes. And then we have the following sequence. Like, so I-dimensional homology of their intersection, and for each A and B, I-dimensional homology and take direct sum. And next, for same dimension, take union. And then next one should be dimension becomes one less. So this is from exact sequence. That's the statement of Mayer-Vitter's sequence. So I asked whether so some students said whether they know what is exact sequence, but they said they forgot. So I'll carefully say the definition. So let's say we have such kind of sequence, and also we have some map. And we say this sequence is exact if corner of fi is equal to image of this map for Ri. Okay, now this is our main tool, and we want to compute homology group for our independent complex. So first of all, we have to express our independence complex as a union of two simplicial complexes to use this sequence. So here's just one possible way. So we're going to decompose this first. Consider this independence complex. So it contains an independent set that does not contain V. And then, so the other part should contain all independent set containing V. So if some independent set contains V, that means that does not contain any other vertices in the neighbor of V. So first take independent set that group G minus close the neighbor of V, and then take join. Here join means that whenever we take a case here and also take a union of this, then it becomes a base of this complex. V. Yeah. So this is just neighbor of V and also containing V. So I will use Mayer-Vitter's sequence for this expression.
We should empty set and
Sorry?
of V is not a complete. Join the empty set and the set of empty sets as V.
Yes, yes. Okay. I mean, usually, if we have two simplicial complex, and take join means that
yeah, because then the subset has to be.
I mean, what he wants to say is that this is a simplex on this vertex. Okay, so now if we use this many orbitals sequence, so first of all, this is our A, and this is our B. And first, B is constructible. Because it is con with apex way. So it is constructible. And also, if we take union of A and B, then it's just independence complex of this graph. Yeah. Okay, so what we can obtain is first of all intersection. And homology of A. And direct sum of homology of B. But we know that B is contractible, so it becomes 0. So we don't have to consider this part. And then now union. So we obtain this sequence. Okay, so we are going to use this. Okay, so now to prove 2, we are going to take a minimal counterexample. Say G. Then G should be ternary, and also totality number should be at least 2. And whenever we take some proper in this subgraph, pH should be at most 1. Okay, so and then so their proof is basically motivated from the previous result of Chodnovsky, Scott, Zimmer, Parker. So their proof idea was so their statement is about this characteristic, and if we can write this characteristic as the sum of -1 to the size of A for our independent set. And we define f sub g of xy as the sum of this, but not our independent set. So consider independent set such that containing x and disjoint to y. And then they prove some recursive formula. Which is
Can you explain the proof of the Cholowski and others?
No.
Oh, this is
just for this. I mean, so this is proof of method of Chodnovsky's their proof, and so the result when Zhang they motivated from this recursive formula, and they made quite similar formula for total Betti number. So here, the true question should be: so can you find? So that was their idea, and to find this kind of recursive formula, they used this Mayer-Vittor's sequence. It's not better to erase. So I will explain this recursive formula for this Betti number. So here's some more notations. So I will just denote this Pi tilde of G is I-dimensional Betti number of independence complex of G, and also we say this kind of notation. This is Betti number of this graph, and here so this is somehow, I mean, motivated from this kind of formula. So consider graph G and minus closest neighbor of x and minus y. If x is independent set and x and y is disjoint. And otherwise, we will say this graph is just null graph. Okay. So now by using this Mayer-Vittor's sequence, so let's say that so here we say that this map is lambda I, and this map is lambda I minus 1. Then what we can obtain from this long exact sequence, so we can find some short exact sequence, which is given as so take a corner of this map, then it should be subgroup of it, and take an image of this and quotient this group, then we have this kind of short exact sequence. And if we have this short exact sequence, we know that the dimension of this middle one is equal to the sum of this dimension and plus this dimension. So what we can obtain from this, so we obtain that dimension of this means beta I of this I of G is dimension of this means and also plus dimension of this. And then also by using dimension theorem, we obtain the okay, then by using the notations, then it is pi tilde of G is equal to pi tilde. So this becomes empty set with by this notation and minus pi tilde with empty set. So I'll use this part just beta of ni. Ni is here corner of I. So we obtain this, and actually now if we replace instead of G, consider G minus plus neighbor of X and also minus Y. Then actually we can change this formula like pi tilde of X by Y is equal to adding Y to the right part. Here add V to left part. Also here should be something similar part. So we obtain this kind of recursive formula for Betti number.
What is ni prime?
So here, ni is a kernel of lambda I. So here we replace G by this graph. So that means there is some also long exact sequence. So there must be some another map lambda I prime. And so it's kernel of lambda I prime.
Then you need, instead of beta, you need a dimension.
Yeah, just simple notation. Yeah, just say dimension. Okay. So and on also here's some easy remark that this dimension of ni prime is bounded by this number. because Ni is a subgroup of this homological group. Okay, we are almost ready to prove. So here's some more annotations. So we use this kind of notation. So here D comes from dimension. So we say this is K if sub K is equals to 1 for this step. So since we assume that our graph G is minimal counterexample, so this implies that for the other dimension, it should be 0. So there is only one possible dimension that satisfies this condition.
So when you assume that x over y is non-empty?
Yeah, non-empty. And it has this beta I or 0 for I, then we just denote this is just star. Then here's some lemma. So first, union of x and y is non-empty, and say the V is not contained in the union of x and y. And we want to compute these three numbers. So this one, and add V to the left part, and add V to the right part. So we want to compute these three numbers, and it always looks like this or star k or this for some integer k. So this lemma used this recursive formula here. So by using this, we can prove now the main result. Is there any question? Is that too fast?
Can you show us how, I mean, for some case, how you sustain one of these four references? To see
Okay.
how many.
So we have this kind of formula. Let's say that if this is k, that means this is 1 if I equals k, and other case it should be 0. So then for k, and also for the other index, let's say that this is star. It looks much complicated. Okay, so it's always 0. So, and then we say that maybe it is equal to 1 and see what happens. Then if it equals 0, then it should be also equal to 0 because, as I said before, it is bounded by this number. And then
dimension is not negative, so the only way you can
yeah,
make
so it becomes also 0.
it's 1, right?
Yes, it should be 1. So if one part is k, then the other part is also k. So because of that, it's either all of them are star or same dimension. By almost symmetry.
What if dk to the xy union is? Oh no, that's I see. Okay. It cannot be 2, right? It's only 0 or 1.
Yeah.
By induction, I see.
Sorry?
Yeah.
Yes, this part is 0 because we assume that this is equal to star.
Oh, I see what you mean. Like, over there it's x y union v.
Oh, sorry.
Over there, so.
Sorry, yeah. I think that must be, yeah. Anyway, yeah, the proof is almost similar. Yeah.
X are y is very defined because you take the minimum quantity.
Yes. And consider only the case that x union y are non-empty. Okay. So here's final claim. So what we want to show is that there is some integer k such that piece of k is 2, and for the other index it's 0. If we prove this claim, that implies our characteristic, that source value should be 2, and it's already contradiction to the statement, yeah, here.
we are trying to prove this conjecture.
Yes,
So we
two.
assume that the graph is ternary, and we assume that the minimum count is level.
But we know that for every ternary graph, the characteristic is bounded by 1.
Oh, so you're still using their theorem.
So actually, they proved without using the previous result, but I will not mention about it because it's still, still complicated, and also the remaining part is, the idea is almost the same. So they just use this lemma. So I will not use.
Are they giving alternative proof of the
Yes, yes. But anyway, I will not mention about that. So the remaining part is almost the same idea. So they just use this lemma. Okay, so let's just prove this claim. Okay, now I will consider total Betti number of G. So by using this recursive formula and take some of our index, then what we can obtain is the total Betti number of this and minus total Betti number of this and plus sum of two times of sum of this. And then we know that this is bounded by this number. So
beta G just means that the total Betti number independent complex of
G, yes. Okay, then it's equal to and by assumption, we know that this is at least 2, and each of these are at most 1. So to express this inequality, actually they are saying 2, and these are equal to 1. And also, dimension of Ni should be so now this implies from the recursive formula. So this towards aim. So what we obtain is this. Okay, now by by contradiction. Assume that there is some two distinct integer k and l satisfies this equality.
because you have some of these numbers to be 2, so
And I will define two vertex subset. So first one is the vertex U such satisfies dimension of this is k minus 1. And also the other set is if we define this vertex set, then you know that every vertex contained either V1 or V2 because of that equality. So here, so it becomes the vertex partition. And what we want to show is to prove so take any x, y subset of V1 and consider disjoint x, y. Then this dimension is k minus size of x if y is empty set. And if x and y both are non-empty, it is just star. And if x is empty, it is equal to L. So that means if we draw some diagram,
Okay, so P1 is P1 is those vertices where the k minus 1 is 0 and the P
so if
k minus 1 is 1 and the other one is 1. So that's
if we contained in V1, then if we take this is k, then it's 1, and this becomes 0 and it becomes 1.
oh, that becomes 0 because L is bigger than K?
Yes.
Well, why you don't have a symmetry? So the second one is L minus 1 and L. So
Oh, sorry. This should be k. If we draw the diagram, so that means it only depends on the size of x and y. So if the size of x and y is like this, and in this case, this dimension gives like is given like this. So this means this diagram. I don't know whether I have enough time. So to prove this, we can assume that we, by induction, until this row, true. And then we compute the next row. So let's say that we know that this row is given like this, and then we want to compute the next row. So first look at this triangle. So I'm gonna use this lemma. So since here we know that this is k minus t, so either this case or should be this case. So that means here should be star k minus t or k minus t minus 1 star by using this lemma. And then also now see next triangle. Then yeah, it should be like this. So next number should be also k minus t, and so on. And here we have final triangle. So if we look at this, it should be this case. That means L equal to k minus t plus 1. But we know that L is bigger than k. That gives t is less than 1, which is contradiction. So this is impossible. That means if we compute this, we obtain this. So the next row should be like this.
This is induction on the sum of the size of x and y.
Yes. So yeah, we are almost done. So by using similar argument, what we can show is to take two vertices in V2, and these two are distinct vertices, then we can compute that it is L minus 2 by using similar method. Then it implies that the U and V are independent set. Because if they are dependent, we define that this graph is null graph, so it's impossible. So that means this holds for any vertex. So V2 is an independent set. So that implies we consider total Betti number of this graph induced by V2, then it should be 0. Because for independent set, the independence complex should be simplex, so total Betti number is 0. But we know that this is equal to this, and by the formula, it is equal to it cannot be equal to 0. So yes, we know that this one is equal to L. So contradiction. Okay, so that's end of proof. And as I mentioned before, so I'm gonna talk about the remaining part. So actually they can prove the main result without using the previous result. And the proof method is almost the same. They use this kind of diagram using that lemma and so on. Okay, this is end of my talk. Thank you for listening.
Thank you very much. Questions?
Yes.
Any similar result for any other graph class, such as four induced cycles are not divisible by any integer.
I don't think so. The conjecture itself is quite looks interesting, and for forest, there's some results about independence complex, and I don't know the other things. Do you know any?
I wanted to ask you what was the motivation of this conjecture.
You know the answer, but you're asking.
You have to ask either Kalai or Meshulam. But my guess is that we know that how for this cycle, we know that how it looks like. So I think that start from that.
That's what I was thinking. So answer that same as Jinha says. So we know that for cycles, maybe induced cycles. No, let's say this. For cycles, we can compute the homology of this independence complex, and probably, yeah, we can compute the homotopy type of this. It's exactly the same as the homotopy equivalent to some dimensional sphere, and we even know the what the dimension is, right?
Yes.
For all cycles.
Yes.
And I think this C3K has that cycle, and for the others other lengths, it was contractible, right?
Either contractible or homotopy equivalent to sphere.
I mean, for length C3K plus 1 or C3K plus 2.
I think it's homotopy equivalent to a sphere.
Oh, okay.
And in this case, it's with the sum of two
Right.
sphere. First and D, depending on K.
So the point of the conjecture, I think, is that you want to define a class of graphs whose in such that for all induced subgraphs, the total Betti number is at most 1, for instance, and then this confirms that it is exactly ternary graphs. The class of such a graph is exactly ternary because all cycles of length 0 modulo 3 doesn't have that property. Right? So now we have even only theorem. Right? So it's complete characterization of the graph classes such that all induced subgraphs have total Betti number at most 1. Then this is the answer. Exactly those graphs are ternary graphs. Because the converse is true, so.
But what happens if we forbid also C3K? I mean, there's a classification. C3K has a 2 Betti number 2, and the C3K is either plus 1 or minus 1. It has Betti number 1, and the other one has Betti number 0. And I wonder what happens if we forbid C3K and the one with Betti number 1.
So you want to forbid a little bit more.
Yeah.
I don't know.
Only allowing the induced cycles of, induced cycles of length, some specific number with the residue divided by 3.
As I mentioned, actually we doesn't know the exact homotopy type of independence complex for ternary graph. So I think we can ask that. And if we prove that, I also want to know that when it becomes contractible. But I guess it's difficult.
I guess if we forbid, Donggyu's question, if we forbid the induced cycles of length divisible by 4, then the result would be very complicated. just my intuition from that observation.
Is there any study of this Euler characteristic of a graph? For example, is there any relationship or bound known with some other graph parameters?
Oh, you mean this number of odd independent set minus number of even independent set?
Or is it just like came as a corollary from this? That's why we talked about.
Actually, I don't know much about this, so maybe Zhang knows better.
So I heard this conjecture in 2013 when I went to Barbados workshop. And then after I returned, I talked to Reinhard Distel about this conjecture. And he had two reactions. One is, why on earth somebody care about graphs without cycles of length 0 modulo 3? And then second is, who cares about number of independent sets minus number? So for graph theorists, it's a bit strange parameter. Now it seems quite natural. Now there may be some new theory. Any other questions? Okay, for now let's thank the speaker.